Hey guys, Mr. B here. In this video, we're going over the Chapter 2, Section 2 notes on mixtures. So in this section, we're going to learn about what is a mixture and how is it different from a substance. And then lastly, how can we separate mixtures? So here we go. There's some vocab here. We'll go through these, of course, as we go through the chapter section. So, but it's going to be important to just be able to distinguish what these words mean. All right, so first up, how can mixtures be classified? So let's take a look at what is a mixture to begin with, okay? So a mixture is a physical blend of two or more components. Now the key part here is this word physical, okay? The word physical and chemical come up a lot in chemistry. And understanding what that word means is really important. Now when you think of the word physical, you might think of like physical, like I'm touching someone, right? Like I'm getting physical with them. I have to contact them. It's not really what it means in chemistry, okay? When we say physical in chemistry, what we mean is something that can be done that doesn't change the composition of the material, okay? So, doesn't change the composition. So, a physical mixture means that the pieces, the things that are in the mixture, when they get mixed together, they're still the same stuff. Okay, we haven't changed them into new things. They still are the same things they were before. They're just now blended together. Versus if they were chemically blended, which we haven't talked about chemical stuff yet, but if they were chemically blended, they would be bonded together chemically and they'd actually be a whole new material. Okay, so mixture is a physical blend of two or more things. A salad bar, for example, is a really good example where there's all these different items and you can put them all in a bowl and you can mix them all together. And those things are all still like their own individual pieces that you could like pull out and stuff. They're just now mixed together, right? So that's a mixture. Based on how the mixture is comprised, there's two ways for us to distinguish them, okay? First way is a heterogeneous mixture. We'll talk about in a second what that means. And then the second one is a homogeneous mixture, okay? The words hetero and homo can give you an idea of what each one of these mixtures is like, but we'll go into the definition for each of these here right now, okay? So, heterogeneous mixture. A heterogeneous mixture is one where the composition is not uniform, okay? When we say uniform, what that means is that it looks different in different parts. Like you can see that there are different things there, okay? So, looks different throughout it. So a heterogeneous mixture, a good example of this could be a salad. Okay, prime example, in fact, just from the previous slide that we just had. So example is a salad. A bowl of cereal is another good example. A taco. Okay, all of these things are like all of these pieces that are mixed together, but if you look at it, you can see that there are different things, right? If you look at a salad, you can see there's lettuce, you can see there's carrots, you can see there's croutons or whatever. You look at a bowl of cereal, I guess depending on the type of cereal, but even then, you can see that there's like, solid pieces of cereal, there's then liquid milk in there, stuff like that. If you look at a taco, you can see that there's meat, and then there might be cheese, and there might be lettuce, and there might be tomato. So these mixtures are all physically blended. So all these pieces are still their own things, but you can also see them, right? You can see that they're different. So that's heterogeneous. Homogeneous mixtures, on the other hand, have a uniform composition throughout it. So what that means is if you look at it, you can't tell that there are different things inside of them. Okay, if you look at it, it just looks like it's just one material. So it's uniform. Again, let's just make sure we put this in our notes here. So it looks the same. It looks the same everywhere. Another name for a homogeneous mixture is what we call a solution. Okay, so examples of examples of homogeneous mixtures. Milk. Milk is a great example. Now, if you've ever seen a glass of milk, which I'm sure many of you have, you probably don't know that in milk there's water, there's fats, there's proteins, there's milk sugar, there's all kinds of stuff in milk, right? But if you look at it, you don't see like all of these little things floating around in there. it looks like one uniform bottle of stuff. Another prime example of a homogeneous mixture would be like Gatorade. Right, again, bottle of Gatorade. If you look at it, whether it's red or orange or blue or whatever, there's water in there, there's sugar in there, there's food coloring in there, there's salts and all kinds of stuff. But again, you don't see all these things floating around. It just looks like one layer of material. So homogeneous mixtures are sometimes a little bit harder to tell that they're mixtures because the materials in there blend together so well. But they are made of multiple parts. And even though, again, they're all kind of dispersed together really evenly, so you can't see the different parts, they are still their own individual things. Okay, so they're still physically blended. They're not chemically combined into a new material. You can still separate them out if you had the tools. Okay, all right. Now, when we talk about mixtures, we use the word phase. Okay, phases are just how we describe the different parts of a mixture. Okay, so a phase is just one portion of a mixture that has the same composition and properties. So in a homogeneous mixture, for example, there's only one phase, which means that if you look at it, everything looks the same, right? So it's just one single phase. In a heterogeneous mixture, since there are multiple pieces there that you can see, you can actually see them, there are usually two or more phases, okay? So, think of, again, like a salad. So we'll use this, again, as an example because salad is just a good example to use. Example, salad. Let's make this unbolded, and let's make our font a bit smaller here so we have plenty of space, okay? So in a salad, we could have, like the lettuce phase. You could have the carrot phase. You could have the crouton. I don't know how to spell crouton. Crouton. I think that's crouton. Crouton phase, right? So in a salad, there's multiple phases. And basically a phase is just describing one portion of the mixture that's all made of the same stuff. Okay, this is just how we can describe a mixture in better vocabulary, right? So, if you wanted to talk about a particular heterogeneous mixture and you're like, oh yeah, that part that's like dark, or that brown part, it's not very descriptive, right? We could go, oh yeah, I'm talking about the lettuce phase in particular, which is just all of the lettuce or all of the carrots or something like that. So, okay. All right. So the last thing here before we'll talk about some questions is, so here's an example. When oil and vinegar are mixed, they form layers or phases. The oil floats on top of the water phase. So we have olive oil and vinegar, which both, by the way, are mixtures. They're homogeneous mixtures, but if you look at them, you probably couldn't tell they're homogeneous mixtures. And then when you mix them together, they make a heterogeneous mixture because now you can actually see the two layers separate from each other. Okay? Okay. Now, if you're wondering, you probably have noticed that I might have skipped past some questions right now. In your notes, you might have questions throughout here. I'm not going to answer any of the questions in this video. I have a whole nother video of me going over those questions. So if you're confused on the practice problems that are in the notes here, go watch that video and I'll explain how to do every single one of them. Hopefully that'll clear up any confusion. But in this video, we're just going to be going over the information. Okay, moving on. So how do we separate mixtures then? Okay. So since mixtures are physical blends of multiple things, it then makes sense that in order for them to be separated, you need to use physical properties. Okay. Now just to remind ourselves what physical properties are, and this is from the last section, or the first section of the chapter. Physical properties are properties of a material that can be tested without changing what the material is made of. Okay. So, examples of physical properties could be like boiling point, melting point. Oh, I can't spell melting. Melting point. Okay, melting point. Density, hardness, color, size, or you say, volume, or that volume, or mass. Okay, all of these things are properties about a material that can easily be tested or checked. And after you test those things, the material is still made out of the same stuff. You haven't changed it into anything new. Okay, so that's how we usually will separate mixtures. there's two processes we're going to talk about here that are pretty common ones that we use in chemistry. So the first one is known as filtration. Filtration is a process that we use to separate out solids from liquids. Okay, the most common type of filtration that you might be familiar with is using a colander to separate out noodles or pasta from water, right? If you've ever made spaghetti or macaroni and cheese, right, and you gotta boil the water, you gotta put the noodles in there and boil them, and then you gotta pour the water off and get all the noodles, right, in one container. Use a colander. And a colander is essentially a big bowl, has a bunch of holes in it, and the holes are small enough that the noodles or whatever can't pass through, but the water can. So filtration is using the physical property of particle size to separate out these two things. Okay, water or liquid particles are much smaller than solid particles sometimes, and so the liquid particles can pass through the holes of the colander, but the solid particles can't. So they get stuck, they get trapped, and essentially then you separate them out. Okay, after you've separated these two things, though, the water or the liquid is still water, it's still liquid, and the noodles are still noodles. Okay, so you haven't changed what they are, which means that it was a physical process to separate them out. Okay, so that's one way. In chemistry, we don't use colanders. We use filter paper. Okay, it's basically paper that has very, very small holes. You wouldn't be able to see the holes with your naked eye, but liquid passes through it just fine. Solids don't. Okay, it's a lot of times how we separate out solids from liquids. Otherwise, another way that we can separate out things is a process known as distillation. So distillation is primarily used to separate out liquids from each other. Okay, so if you have, like, let's say, for example, a mixture of tap water, which, probably has, it's water, and there's probably some salts in there, and there's other minerals and all kinds of stuff. And we want to separate, we want to get just the water out. Distillation, what we use is we use boiling point and condensation point, okay, to separate these things. So you have a container here, which has liquid in it, and you heat up the liquid. And as the liquid heats up, it will start to boil off. And as it boils, then it will travel up this tube, and it will go down what's known here as a distillation column. Okay, it's basically a tube that has like an inner tube and then an outer tube outside of it. You run cold water around the outside of the tube, and then the inside tube, which has stuff going through it, the water doesn't contact. So as the gas which boils off comes down and goes through the inner tube, cold water goes around it and it cools the gas down and condenses it back into a liquid. And then it drips out on this other side into a container that you put there. And you now have the liquid that was, originally over here, now in this container, completely separated from whatever else was in there. Okay? Because the solid particles like salt and stuff they don't boil into a gas. So they stay in the original container. But let's say, for example, you had a container of a lot of different liquids, so no solid, just a bunch of liquids. Let's say you had water and alcohol, right, or ethanol, which easily dissolves into water, and you wanted to separate the two. Well, ethanol or alcohol boils at a much lower temperature than water does. So if you started to heat up the mixture of water and alcohol, the alcohol will boil first. Okay, so you get the temperature to like 89 degrees Celsius or whatever. The alcohol is going to boil off as a gas. The liquid, water, will stay here in the container as a liquid because that's not going to boil till it hits 100. So the alcohol boils off at, say, like 89. It then goes down the column. You condense it down to a liquid. And over here, now you have pure alcohol in a container that you've collected. And back in the original container, you have still the liquid water that is there. Hasn't boiled off yet. And you could then boil that one off and condense that one and collect it into a different container. And now you have the liquid water and the liquid alcohol in separate containers, and you've separated them from each other. And again, there's still water and there's still alcohol. So you haven't changed them into new materials. So it was a physical process, and therefore it was a mixture, right? Because they were physically blended. So again, very common thing that we do in chemistry. So okay, again, there are some problems here. We're going to look at this one example one here, but then the rest are practice problems for you to do, and there's a video of me going over those. So let's take a look at the one example problem here, and that'll be it for this video. So it says here, separating a heterogeneous mixture. So it says sometimes plastic signs are used to mark trails used by bikers or vehicles. The sign in this photo is used to mark locations along a trail. where an all-terrain vehicle or an ATV or a four-wheeler or whatever you want to call it is permitted. Aluminum nails are used to attach signs at eye level to trees or posts. How could a mixture of aluminum nails and iron nails be separated? So let's say you got a big bucket of nails, right? Some are aluminum, some are iron, and you need to use the right ones for your signs. How can we possibly separate them out? Because they both probably just look like silver nails. Well, there's a lot of different properties that we could use to distinguish between iron and aluminum. Color probably isn't one. They probably both look the same color, so that's not going to be a good one. Particle size, probably also not going to be good. The nails are probably the same length and the same size, so that one won't work. Density, we could try using density. I'm sure iron is probably more dense than aluminum, so you could determine the density of each nail individually and know, oh, that's an iron nail because that one's more dense. That's an aluminum nail because that one's less dense. Now that would take quite a while, so it might not be the best way to do it, but it is at least one way to do it. The best way, however, to do it would probably be to use magnets. Iron is magnetic. That's a physical property of iron. It's a physical property because if you take a magnet and you stick it to a piece of iron, the iron will stick to the magnet and it's still iron. Okay, just by putting a magnet on it, you haven't changed it into some different material. It's still going to be iron. So you could take a magnet, you could stick it in there. All the iron nails, of course, will stick to the magnet, and all the aluminum ones will stay in the bucket. Then you pull all the iron ones out, and all the aluminum ones stay in the bucket. You've now separated them out, and they're still iron nails. They're still aluminum nails, right? Piece of cake. So that's just one way that we could separate this mixture. There's other ways too. Like I said, density would be another way, but magnetism is probably the easiest. So, okay, that's it for this section of notes. Hopefully that helps you. Again, I have a video of me going over the practice problems, so if you want help on those, go watch that one. And otherwise, if you have any questions, as always, feel free to email me, reach out, we can chat. Otherwise, I'm Mr. B. That's the second section of Chapter 2. See you in the next one. Bye.